Fairly often, I get asked questions about how I got started podcasting with the Breaking Math podcast, and I'll often be asked this question by those who are thinking of starting their own podcast. That is, people who are looking to tell a story or share their unique wisdom with a larger audience or their passions, or maybe just advertise their business or services. I usually like to start this conversation by either showing off or telling about our preferred podcasting platform, Zencaster. Zencaster is essentially an all-in-one podcast hosting platform. On this platform, you can do everything from recording your episodes to editing your audio and video files to distributing your podcast to all podcasting platforms, including Apple Podcasts, Spotify, iHeartRadio, and wherever else podcasts are played. Now, there's more. When I first began podcasting, I used to get very nervous about how I would sound. I would sometimes stutter or have awkward pauses or other audio blemishes in my recordings. Now, Zencaster has a new suite of AI tools in their post-production process that make you sound really smooth. They automatically take out any of the ums or ahs in your recording. Also, they automatically take out any of the awkward pauses in your discussions. The tools will also help you set the right loudness and balance all the levels while reducing any background noise, all with the click of a button. Doesn't sound too bad, does it? You really should check it out. Really, the world needs to hear what you have to say. In fact, I'm going to give you a code below to help give you a large discount. It's all one word: Breaking Math. Go to zencaster.com/pricing and use my code BREAKINGMATH, and you'll get 30% off of your first month in any Zencaster paid plan. I want you to have the same easy experience I do for all my podcasting content needs. It's time to share your
Summer concerts, pool parties, chill nights under the stars. We're stocking up our closet so you're ready to look your best for all of it. At Plato's Closet in West Ashley and North Charleston, we're buying all things summer. So bring in your tees, tote bags, sandals, sunglasses, and more. We pay cash on the spot for gently loved name brand looks. Plato's Closet is the go-to destination for trend-forward teens and young adults who support local and shop sustainable. Visit Plato's Closet today. Plato's Closet, located in West Ashley on Sam Rittenberg Boulevard and North Charleston on Rivers Avenue.
From MC² statement of mass energy equivalence and Newton's theory of gravitation to the sex ratio of bees and the golden ratio, our world is characterized by the ratios which can be found within it. In nature as well as in mathematics, there are some quantities which equal one another. Every action has its equal and opposite reaction. Buoyancy is characterized by the displaced water being equal to the weight of that which has displaced it, and so on. These are characterized by a qualitative difference in what is on each side of the equality operator. That is to say, the action is equal but opposite, and the weight of water is being measured versus the weight of the buoyant object. However, there are some formulas in which the equality between two quantities is related by a constant. This is the essence of the ratio. So what can be measured with ratios? Why is this a topic of importance in science? And what can we learn from the mathematics of ratios? All this and more on this episode of Breaking Math. Episode 20, Rational. I'm Jonathan.
And I'm Gabriel.
And you're listening to Breaking Math. And today we're doing an episode on ratios.
Yes, ratios are all over the place in mathematics and in physics. This is a very exciting episode.
Yeah, in a way, all a ratio is it's so simple that the word comes up in the definition. It's a ratio between two quantities.
Mm-hmm. So obviously in this episode, we can expect to first talk a little bit about ratios, what they are and why they're important. Also, what are some of the important ratios that we'll be talking about?
And we use ratios every day. Gasoline, for example. The price of gasoline is a ratio between how far you go and how much money you spend going that far.
Yeah. What are some of the ratios that we'll be talking about today?
Today, what we're going to be talking about is, of course, the gravitational constant. We're going to talk about phi, the speed of light. In fact, all the physical constants we're going to be talking about. We're going to be talking about mathematical ones like pi and phi, which was already mentioned. And yeah, that's pretty much the gist of it.
Yep. Alrighty, without further ado.
So, of course, ratios are important just because there's no other way to relate two numbers through multiplication,
From my perspective, which is, of course, a 33-year-old engineer who was also a teacher, I have certainly a profound appreciation for ratios. If you asked me when I was in 7th grade, I would have pretty much only thought of them as mathematics. But, of course, almost all of physics is, of course, ratios. That is, physics equations. So, that's everything from E equals mc squared. That is Newton's force equals mass times acceleration, everything that is described as an equation, of course.
Like the dielectric constant when you're doing capacitors, or the springiness constant, elastic constant, that you could modify at will. So you have two different types of ratios, essentially, but the takeaway is that they're important.
Yeah. In the case of all the constants, it's always one thing per something else. It's always those units. Do you know right now offhand what the dielectric constant is in?
I do not. It's volts per something. I don't know.
Put you on the spot there. But the point is that a ratio, of course, is a description of a relationship. And that's very, very important when we are going to make sense of the world around us.
So we're going to give the example of E equals mc squared and show what that is. So you have on one side energy and the other side you have mass.
Yeah, I just love it. I think I was in middle school when I actually considered the fact that you can have a description where you have mass times the speed of light squared, and the fact that that is equal to energy as shown in this equation. The profoundness of that equation can't be understated. Jonathan, I think that one of these days you ought to do a full podcast, in fact, on that equation, or at least the math behind it. What do you think?
Oh, yeah. Maybe it might be in the next episode. But also another one is gravity. So for gravity, and this is something that actually guest Zach brought up on the language of the universe. When you do gravity, you multiply the masses and you divide by the square of the distance between them. But that's not all you do. You have to have a constant. In this case, the gravitational constant. Mm-hmm. And the gravitational constant is in really weird units. I remember trying to make sense of them, and it's very difficult to do.
This reminds me of another idea I once had. I wanted to do a whole episode on just our favorite equations, and that's one of them. The other one of my favorites that I'd like to talk about is Stephen Hawking's information paradox. It also has the gravitational constant in it. That's quite a profound equation as well.
Oh yeah, definitely. Perhaps one of the most famous ratios is known by the name phi, and is related to the Fibonacci sequence, which is found all over nature. Simply put, phi is a number such that the ratio between phi and 1 is equal to the ratio between 1 and 1 over phi. Intuitively, what this means is that when you multiply phi by itself, you get 1 plus phi. Multiply that by phi, and you get twice phi plus 1. Any round power of phi can be made by multiplying phi by a whole number and adding another whole number. It has been renowned since antiquity for its aesthetic and mathematical properties. Where can we find phi, for example, in the human body?
Ooh, there's a lot of places, actually. Take a look at your arm. You'll notice that your forearm is a little less than half of the length of your entire arm. If you were to measure this, usually you'd see that the ratio between the part of your arm that is not your forearm and the forearm is actually pretty close to phi, in fact.
The golden ratio, golden spiral, all these things, you've probably seen them online. And really a lot of that is, unfortunately, pseudoscience. For example, the Parthenon, if they measured phi, it was not very carefully, and Greeks are nothing but careful when it comes to math.
Yeah, and actually, when I was younger, I also learned that the Parthenon is actually equal to phi. Now, the truth is that it's not, in fact, equal.
It's only within like 1 decimal point or something like that, 1 or 2.
Is that a mistake that we can forgive the Greeks for, or should they have known better by then?
Well, I mean, they had advanced enough engineering to make big old pillars and things like that. They knew how to measure.
I see. Okay.
And they could have constructed it using a straight edge, which is something they would have done.
Interesting. Yeah, then I wonder how that got pulled off. Maybe they thought nobody would notice.
I think the answer is it just happens to look aesthetic.
Yeah.
The ratio phi is very pleasing to us, so we tend to approximate it, but it's not like an exact science.
Now, we talked earlier about the forearm. This was first introduced to me when I took an art class. I think it was in high school. I'm always alluding back to school. I can't help it. That was a very meaningful time for my first introduction to math and science, so I'll probably keep doing that. We were learning about Renaissance art, and I think it was Leonardo da Vinci and his Vitruvius Man. And I think that one of the reasons why his art, as well as the sculptures of ancient Greece, were so realistic looking and so beautiful was that they oftentimes used the approximations that are related to phi when creating the arms and the fingers and things like that. Even with the fingers, I believe, isn't it the digits of your fingers, they also get smaller according to phi?
Oh, yeah. And one thing you did mention was with Vitruvian Man. A common misconception about the Vitruvian Man is that it was made to illustrate phi. It was made to illustrate squaring the circle. He thought that he found a way to do it using the human body.
Oh, okay.
But it does have phi embedded within it, and that's what makes phi so confusing. You never know if it's there or not, unless you have really accurate measurement.
It's fascinating how that just pops up all over the place in Renaissance art. I've also, I've seen a lot of people who will put a Fibonacci spiral in art, and sometimes I think they just kind of stick it on there, whether it's there or not.
Oh yeah, I've seen it in ridiculous places.
I've seen pictures of I think in a courtroom there was a big argument happening and people were fighting, and somebody decided to just draw a Fibonacci circle over everyone's head, and somehow it touched everyone's head or something. But that's
it's silly.
Yeah, it is. So.
And we're going to talk really quick about the Fibonacci sequence. So with the Fibonacci sequence, you start with 2 ones, right?
Yes. Actually, is it fair to say that you start with 0, or are we not
it depends on where you start counting.
Okay.
Because you could do the Fibonacci sequence backwards too. We won't explain that, but we'll explain how to do it forwards.
I love the Fibonacci sequence, and I think that to really capture the beauty and the relevance, perhaps some of the videos available online might be necessary, or rather not necessary, but suggested, of course.
Oh yeah, absolutely. Just Google Fibonacci sequence in nature.
So you start with 1, and the basic pattern is basically you add the previous amount.
Yeah, so you have 1 and 1, and then 1 plus 1 is 2.
Yep.
So you take the first one, throw it away, and you're left with 1 and 2. 1 plus 2 is
3.
2 plus 3 is
5.
3 plus 5 is
8.
8 plus 5 is
13.
and so on. And
that's,
And what's cool about that is that, let's say we have a really high Fibonacci number, like I think 144 is a highish one, and you divide that by 88 or whatever the previous one is, you'll get closer and closer to phi.
And that's the higher up you are in the Fibonacci sequence.
Yeah, for those of you who are in calculus, if you have f of n being the nth Fibonacci number, then limit n approaches infinity of f of n plus 1 over f of n equals phi.
I'm sure you all caught exactly that, right? Did you all catch that?
I hear crickets.
That's another fascinating number. Also, limits. Those are also quite a concept. I have a hard time when I imagine infinity or try to think of infinity. So the fact that we use it all the time in limits is trippy.
In ancient Babylon, there's a number very important to engineering. This number was 3 1/8. This number was about 0.5% away from being correct, and has been ingrained in the heads of high school students as a noble constant pi. The Greek symbol is used to represent a ratio between a circle's circumference and diameter, but it shows up in places where no one would reasonably expect it. For example, if you take the constant e, which deserves its own episode, and raise it to the power I times pi, you get -1. So that's one of the weirdest places it shows up.
That is oftentimes considered one of the most beautiful equations. I've seen that written about many, many times. And that's Euler who discovered that, right?
I believe so.
Leonard Euler. Fun fact, my PlayStation Network sign-in name is Leo Euler 2718, named after the famous mathematician himself.
You're going to get some people joining you on PlayStation.
That's fine. I haven't had a whole lot of time to play recently, but that's totally fine. You can say that you heard about me here.
So one cool thing about pi, should we introduce the concept of hypersphere?
Hypersphere, just that name itself sounds pretty awesome. I think we should.
All right, so what's a two-dimensional sphere?
So a two-dimensional sphere is like a slice of a sphere. It's just a circle.
What's cool about that is that you start with a point, and every other point that is less than a certain distance away from it is included within that circle. So if a point is half a foot away from the thing and the circle has a radius of 1 foot, then it'll be in the circle. Otherwise, it's not. So that's how you could define a sphere. So a 3-sphere is just the same thing, but in 3 dimensions.
I'm going to say what you said, but in maybe a slightly different phrasing. When you asked me what's a 2D sphere, and then I had mentioned what is a slice of a sphere, it depends on where you take that slice. If you take it at the very, very end of it, it is just a single point. But if you move any length whatsoever from that point toward the center of the sphere, for instance, or the opposite end of the sphere, then you have an actual circle.
The end of a sphere would just be, a point in this case would just be a circle with radius 0.
Okay.
Because just the definition of a sphere or a ball, I can't remember which number you use for which, has to do specifically with what's called the neighborhood in the space that it's in. So basically the collection of all points happen to be less than a certain distance away from it.
You know what? I actually love that, because right now you actually put what might seem like an arbitrary distinction, but it's meaningful. I said it was just a point, and you said, well, no, technically it's a circle of radius 0, which I would think of certainly as a point. But the distinction's important.
It's ontologically weird, for sure, but yeah.
It's all about 0. There's a great book by, the author is Charles Sheaf, I believe. It's called The Biography of a Dangerous Idea. You all should read it. It's great.
Oh yeah, it is a good book. All right, so quick geometry lesson. If I have a gingerbread man, and I know that his smile is 1 unit across, and I know that the gingerbread man uses a certain amount of dough, and we're assuming that this gingerbread is like infinitely flat, then if I had another gingerbread man identical to it, but the distance between its smile was 2 units, it would have 4 times the area as the previous gingerbread man, because you take a measure and then you raise it to the second power. Same thing with the volume. So if you made the cookie thicker as well, it would have 8 times the dough. Am I making sense, Gabriel?
I am sort of following, but I'm also getting really hungry too. So maybe we can do a quick recap of that.
Sure. So let's say I have a weird shape, and I know that it has a certain area.
Should we just say a shape of like a teardrop or a shoe even? Because a shoe. Okay, sure, a shoe.
If you have a cutout of a shoe, and if you have a cutout that is twice as long in every dimension, then you use 4 times the amount of paper.
Okay. Yes, I am following.
But let's say we have a sculpture. If I make it twice as long in all 3 dimensions this time, it'll have 8 times the volume.
Yes. Okay, I get it. So this is a matter of dimensions versus volume.
Yeah, and so we know that for a circle, there must be a certain constant relating the radius to the circumference, and it happens to be pi.
Okay.
I mean, not the radius to the circumference, the radius to the area, which is also the radius to the circumference, and that happens to be pi. So you might think that for a sphere, it would have to be something else, some other constant, because they're related, but nobody knows how related they are until Archimedes of Syracuse.
Who deserves his own episode.
Oh, he does.
That's going to be a whole thing, just saying so-and-so deserves their own episode. But it's true. They absolutely do. And the fact that we keep seeing these repeated themes everywhere. Oh, everything deserves its own episode. It's like the Oprah Winfrey of mathematics. You get your own episode. Okay, I'm going to stop.
Yeah, 4/3 pi r cubed is the formula for the volume of a sphere.
Right.
A 6-dimensional sphere is equal to 1/6 of pi cubed times a radius squared 3 times. So okay, it gets a little bit complicated, but it's still pi cubed. So for example, the volume of a 6-dimensional sphere is equal to 1/6 of pi times the radius to the 6th power.
Real quickly, I just want to slow down just a bit because I think the idea of hyperspheres is awesome. Of course, you may recognize the hypershape hypercubes from a previous episode, actually our very first minisode. I think it was called Hypercubes and Other Stranger Things. But with hyperspheres, real quickly, is there a way that we can visualize just going from a 3-dimensional hypersphere to a 4-dimensional hypersphere, and those are all 4 spatial dimensions, just so that we can have a stepping stone up to 6?
Sure, there's actually a good example. If you've ever blown up a balloon, you see how it kind of goes big at first and then it gets bigger more slowly.
Yes.
So if you imagine blowing up a balloon and then letting the air out of it, that's what a hypersphere traveling through time would look like.
Yeah, interesting. So is that sort of like, if you had a single line in 2 dimensions and you had a circle pass through it, that line would experience the point of the circle and then it would experience the circle itself and then it would leave it.
It's also the same example that you had earlier, actually.
Oh, nice.
When you cut a 3-dimensional sphere, you get a 2-dimensional sphere. Yeah. So when you cut a 4-dimensional sphere, you get a 3-dimensional sphere if you cut it with 3 dimensions.
That's the only way. That's literally the only way that I can even begin to fathom hypershapes is I have to imagine what I'd experience if a shape of a higher dimension passed through the 3rd dimension in time.
Oh yeah, for sure. And for more on hyperspheres, we might be coming out with an applet soon, in addition to the hypercube applet.
Not only an applet, but I think that very soon we should have a whole series of posters and maybe some wallpaper and stuff that has not only hyper shapes, but also the equations that go with them.
Look out for that. And we talked about Gabriel's trumpet on another episode, but that's when you revolve a certain graph around the center, the graph of 1 over x, and take the volume from 1 to infinity, you get pi.
Yeah, I've said this before. Ratios essentially is, what does it not pertain to? I think you even have on the Facebook page, you did some mathematics, some art inspired by math, and you used a program on your Mac, isn't that right? Using just Grapher and just ratios with, I think it was sine functions and, a couple other things.
Oh, yeah. We have that up on our Facebook page at facebook.com/breakingmathpodcast.
It's pretty cool.
And it comes up in weird places, like we said before, like the Mandelbrot fractal near -3/4, and then just a tiniest little bit away from 0. You get pi in a complicated way that we can't go into.
You know what? What's kind of interesting is I'm not a mathematician. At least I don't consider myself one, although I'm a great appreciator of mathematics. When people discover pi in those places, it makes me wonder what else you can infer about mathematics knowing that pi is there. So in other words, what other properties of circles and spheres and in the mathematics of spheres also show up in the Mandelbrot set? You know what I mean?
Oh, yeah. It might be related and it might not. And that's definitely a good field of research, though.
Yeah, absolutely.
Humans are a little bit obsessed with the accuracy of pi, and let me tell you exactly how obsessed we are. If we had 100 digits of pi, just 100 digits, which you can memorize in an afternoon, imagine, if you will, the Earth being the size of a grain of sand. The sun would fit in your hand and be about 30 feet or 11 meters away. Pluto's orbit would be about half a kilometer or a quarter mile away from the sun. Walking this orbit at a steady pace would take you 620 centuries, going back to the actual solar system, and takes Pluto itself 248 years. So we're talking a vast distance, right?
Yes.
These are things going kilometers per second and things like that.
Yeah.
So to measure this orbit to an accuracy of 1/trillionth of the width of the finest human hair would only require, if Pluto's orbit were entirely circular, 30 digits of pi.
Oh my gosh. Wow.
So there's no reason to keep calculating digits, but it's fun.
Yeah, interesting. Wow. When you say things like that, I think that I'll never get bored as long as I've got mathematics, right? On to the records. Babylonians had 1 decimal point of accuracy 3 millennia ago.
And then Archimedes, we talked about him before, got 3 digits from the circumscription and inscription of a 96 gon around 250 BC.
That's the termination right there. He basically just, I think he started with a triangle. Was it a triangle or a square? He just kept adding angles.
What he did was he took a triangle or a hexagon and just kept dividing it up. There's only a certain number of ways that you could divide a circle. So you can't make, for example, a 9-gon perfectly.
You know what's interesting? Quick side tangent. Suddenly hearing how Archimedes did this or discussing it, I kind of want to make a computer program that does that same approximation. And this raises the question, why on earth would I want to make a computer program that finds pi through the method of exhaustion? Well, my answer is, why the heck not? I don't know. I think it would be fascinating to do. You know what I mean? Like, that's just...
Oh, yeah. It's not very fast, though. There's much faster algorithms.
Yeah.
So, yeah, let's just run through these. Next one.
Oh, yeah, sure thing. So, this is interesting. Liu Hui got 5. He got 5 decimals in 263 AD.
So Madhava of Sangamagrama got 10 in 1400.
And then Snellius got 38 in 1621. Do you suppose he got made fun of as a kid for his name?
Oh, that was his Latin name. His real name was something like Snell.
Okay.
Which is not better. Okay. So then John Wrench and L.R. Smith got 2037 on the ENIAC in 1949. And let me just point this out.
Yes.
The ENIAC is insanely difficult to program, and writing this kind of program would be really difficult. So hats off.
Wow. Okay. And then we had a gentleman by the name of Francois. I'm going to say this correctly.
I think Gnui.
Gnui?
I have no idea.
Yeah, I'm so sorry. Okay, wow, I haven't even counted how high this is. So is it 22,459,157,718,361 digits is the current record of pi.
And remember, 30 digits is enough to do the whole human hair in Pluto's orbit thing. This episode is all about ratios and their importance in math and physics. To that end, our partner Billion.org has a chapter in the Algebra Through Puzzles course about rate and ratios, which helps you learn about proportionality and apply them to solving circuits. I love the problem in advanced circuits about infinitely many resistors in series and parallel. I was excited to see the golden ratio appear. Actively working through this problem is an invaluable exercise that you don't usually get. To support your educational journey in math, go to brilliant.org/breakingmath and sign up for free. The first 200 Breaking Math listeners get 20% off the annual subscription, which you've been using. And now, back to the show. As has been previously stated, there are ratios to be found in the natural world. The ones that we'll be discussing in particular are known as universal constants.
Universal constants are fascinating. These are a very, very important thing to talk about when trying to get an understanding of physics and the universe that we live in. How would you describe the importance of universal constants? Would you say they're kind of like the main controls in our universe?
To me, they're kind of like when you're making a smoothie. You put in some strawberries, but then if you put in too many strawberries, it gets icy, frozen strawberries. If you put in too much kefir, it gets gloppy. So getting the ratios right, I'm doing a lot of food things I must have not eaten, but it's basically the way that things stick together in the universe. Gravitational constant, Planck's constant, all these have to do with not only how things stick together, but how much more important certain types of thing are.
I like that. One other way of looking at this are these are things in the universe that do not change, hence the name constant.
And we measure them all the time.
Yeah. What actually really fascinates me while I'm looking at these constants that we're about to name here in a few is a belief by a 20th century physicist by the name of, I believe it was Enrico Fermi. Is he the one who believed firmly that there was a profoundly deep relationship between the universe itself and the entire field of mathematics?
I think you are skipping ahead a little bit. I think he's the one that believed that 137 was the exact inverse of the fine structure constant.
Okay. Well, yeah, I don't want to get too ahead of myself, but it certainly illustrates the awesome relationship between mathematics and physics.
So first, we're going to talk about the gravitational constant, and that's equal to 6.67 times 10 to the negative 11 meters cubed per kilogram per second per second. So it's a stupid unit. It's bizarre. It's only used to justify the formula.
Indeed. You multiply it by a planet's mass and divide it by the radius between wherever you want to find the strength of the field, and that gives you the surface gravity.
Well, you have to divide it twice, so by the radius squared.
Thank you. I'm so sorry. I stand corrected. That is correct.
And so that's an extension of the formula. If you take the mass of the Earth and divide by the radius of the Earth, you get the surface gravity of the Earth, which is kind of cool.
Yeah. And again, let's say who was the first physicist? I'm sure this is a pretty famous one. Not one of your favorite guys. Who was the one who first penned this down?
I don't remember his name, but he was Arabic, the first guy to discover the universal gravitational thing. He was rediscovered by a guy named Newton.
Yeah, rediscovered, not the original one. And regarding the gravitational constant, who was it that introduced it?
Well, the gravitational constant was not known until way after that they started using it, actually, because nobody knew the density of the Earth, but Newton used a formula that required it.
Okay.
I think it was about 100 years, actually, before it was measured.
Interesting. Basically, he was trying to describe the speed of the acceleration of something falling, and he needed it.
More like the attraction between two objects, the universal theory of gravitation.
Okay.
That's the one that requires a gravitational constant.
Okay.
And so this one guy built a shed, and he had like a dumbbell type thing hanging from a thread, and he looked at it with a telescope, and he looked at how much it twisted when two weights were placed next to it.
My goodness, that precision is just remarkable. And when was this?
Like the 1700s. And what's even more insane about that is there was a bunch of surveyors that were measuring a mountain because they noticed that there's different gravity on the top and the bottom of the mountain. So if they knew the exact volume of the mountain, they could calculate the gravitational constant, and they were less accurate.
Oh my goodness, this is just insane.
It's one of my favorite experiments because it's pure.
Yeah. Now, I'm sorry, are you referring to the mountain one?
No, that one's very busy.
Okay, interesting. Wow, just to think that somebody would even think to look at a thread with a telescope. Oh my goodness, and this is, again, forgive my quick tangent, but this is relevant. When I think about the shape of a bell, I think it's relevant because he didn't choose that shape arbitrarily. There's a reason why he chose it, right? Is it the weight distribution?
Well, it wasn't a bell, it was like a dumbbell type shape.
Oh, okay.
So they have two masses apart from each other.
Sure. I suppose any shape that would have worked as long as it was...
It was important that the center was close to as massless as possible. And he basically had two weights opposing one another, twisting.
I see. Wow, that's fascinating.
Then we get, what's the next constant?
This next constant is quite a game changer here. It's Planck's constant.
So it's equal to 6.63 times 10 to the negative 34th joule seconds. And to tell you how little this is, there's a thing called action in physics, which is basically measuring things that are moved. It's hard to explain. It has to do with functors.
I'm sorry, what are functors?
Things that map functions onto numbers. So in goes a function, out goes a number.
Okay.
And this is 1/10 of 1/millionth of 1/billionth of 1/billionth of 1/billionth of the action of a baby crawling for a second.
Wow, that is tiny.
Yeah, it's like nothing.
Now, Planck's constant is interesting because this particular constant was arrived at by just an act of desperation from the physicist Max Planck. Do you remember why he came up with this number?
It was just to explain the data that he was kind of got fit the formula to empirically. Wasn't that correct?
Yeah, well, so he was tasked with something. He was tasked with trying to find a way of describing, I think it was luminosity from a German light bulb company. They didn't have a standard way of describing it. And while he was trying to do it, he ran into something called the ultraviolet catastrophe. I don't know if you recall from the physics book.
Oh, yeah, for sure.
Yeah. So the ultraviolet catastrophe is using the only way that he had at the time of describing how bright something is. The higher the frequency, the higher the energy went, just until it went to, was it infinity, I believe?
Yeah, infinity for certain. So basically, it described an impossible situation.
Yeah.
And wherever you find infinities and zeros, you discover things.
Yeah. Now we're gonna have to actually talk about the equation itself, but essentially, when he inserts this Planck's constant, which is such a small number, it changes it, but it has drastic consequences in the world of physics.
It's principally to measure the energy of a thing of light. So you just multiply by the frequency to get the energy. Mm-hmm. This is describing the frequency, and frequency is really discovered through Planck's constant of light and things like that. I don't think it was actually discovered through it, but it was related to that.
I want to talk about Feynman. Didn't Feynman have an example of energy and how it's measured philosophically?
Oh, yeah. So he gave the example of having blocks in a room. So you have like 20 blocks in a room, and then one day you go in there and you see 16, but then you see 4 on top of the bed. And the next day you only see 12, but then you see the chest of drawers closed. So then you assume that there must be a certain amount in the chest of drawers, and that assumption never leads you wrong. So empirically, we know that energy is never lost or destroyed. And I thought that was just an interesting anecdote.
Oh, okay. I like it. Oh, wasn't there an analogy about smoke? Like smoke blown off a cigarette is white. But
oh, yeah, the classic example. Smoke is white when it's exhaled, but it's blue when it's not because of the wavelength of light and the size of the smoke particles. The smoke particles are so small that the red light skips them or is diffracted, and you see the blue light. Or vice versa, and white because then it's just evenly spread.
Yeah, and speaking of that, with respect to frequency and wavelength can be anywhere from multiple kilometers all the way down to less than 10 picometers. Next constant here is the speed of light.
Yeah, and that's 3 times 10 to the 8th meters per second. So it's obviously very fast. So many things would be different if we lived in a world with a small speed of light. There'd just be less energy for equivalent mass, so the balance of mass and energy in the universe would be completely thrown off.
And didn't Ole Rømer first showed that it was measurable by studying Jupiter's moon, Io?
Oh, yeah. He measured it using the shadows and the exact times that you could see the moons. It was crazy. Yeah. It was like in the 17 or 1600s.
Now, I actually want to talk a little bit about the speed of light, and I'm going to talk about a rotating mirror experiment. There was a gentleman by the name of Physio. All right, here goes a whole mouthful. This is going to be like a Texas steak challenge of a podcast. We got a lot of information that's about to come at you. So this is Physio's rotating mirror experiment. You want to take this one?
Sure. So you take a beam of light and you send it to a mirror, which reflects it right back. So it's just bouncing right back and forth, right?
Yep.
So you observe this using an eyepiece, resting above a semi-transparent mirror. So that's a mirror that lets half of the light through and half of the light not through. It actually splits up the photons. Mm-hmm. Angle of 45 degrees, so it reflects the beam like at a right angle relative to the beam.
Yeah.
So then you put a gear halfway between the light source and the first mirror. And they're really far apart. So we're talking kilometers. So when light leaves the source, it passes through the gap between the gear's teeth. And then the gear is rotating, by the way. So it's really quickly, like 720 things per second. And it has tons of teeth. So the packet of light goes back to the eyepiece in the source. The gear has turned such that half of the light is eclipsed by a tooth on the gear. So basically, it's going all the way through the first time and only half the way through the second time. And then we observe that using our human eyes. Foucault actually improved on Fizeau's technique by making the mirror itself rotate and measuring the deflection of the beam. So you could actually measure the speed of light is the takeaway, I guess.
Oh, wow. Yeah, that was quite a mouthful. Okay. There's lots that we can talk about with this constant. Squaring and multiplying by mass gives the energy inherent to that mass, which was introduced by Einstein.
Equals mc squared, basically.
Mm-hmm. And of course, dividing by frequency gives the wavelength, which is an intrinsic property of any object, but most intuitively particles and photons.
Yeah, so I can't remember what the name of this wavelength is, but everything has it.
Yeah, fun fact. Even matter has a wavelength as well.
I think that it comes into play practically in mass spectrometry, which if you ever have taken a drug test, a really expensive drug test, you've encountered.
Is it really mass spectrometry on those? I had no idea. I assumed it was just straight up chemical.
Well, half the time they use enzymes, and but if they're doing like a police test, they use mass spectrometry.
Oh, okay. Interesting. Okay. I was thinking that was related to the electrons and not to the actual matter itself. I'm actually talking about like neutrons. Neutrons themselves have a wavelength.
Oh yeah, I'm talking about the wavelength of the actual molecules, because mass spectrometry, what that is, you pulverize a thing,
yes,
and you weigh the individual things that come off of it.
Yeah. I think
the individual atoms.
Yeah. In fact, and then again, the part that I was getting at that was just nuts was I believe it was the French physicist Born. Actually, he was the one who said, okay. So if light has a wave particle duality, then certainly particles have a wave particle duality too, and he was correct. It's a pretty wild idea, but it's true.
Yeah, and so we're going to move on now to the elementary charge. And what's that equal to?
That is equal to 1.602, and then some, times 10 to the negative 19th coulombs.
So that's a fraction of 1/millionth of 1/millionth of the charge that you get from combing your hair. Now I want to point something out about these.
Coulomb. I'm just kidding. Sorry.
Some constants are large, like the speed of light. I actually think it might be the only large constant compared to the other ones. And the other ones are very, very tiny.
Yeah, these are absolutely small. This is a quick side note. Do you remember how elementary charge was discovered?
Yeah, it was the Milgram oil drop experiment.
Millikan, is that his name? And there's a little bit of controversy about that, both in terms of if it really was Millikan or some say his lab assistant. Now, again, this is a bit of a side note, but I think there's a little bit of controversy as to whether it really was Millikan or perhaps his lab assistant. Perhaps we won't get into that now. But also, was his measurement value accurate, or has it been modified since?
Oh, it was pretty accurate. It was a little bit low. And Feynman pointed this out. The experiment subsequent, it kept getting higher and higher, but it approached a tangent line, basically. Mm-hmm. And as Feynman pointed out, we have modern ways of dealing with that kind of bias that we use all the time.
Yeah, and basically what he did is he had charged particles on oil drops, and he designed them to drop. And I think what he did is he measured.
He switched the thing on and off, and then he had to suspend a drop of oil next to a microscope. It was difficult.
Yeah.
And it's one of the most physically meaningful universal constants, but it might not be the fundamental, as we will see in a sec. What we mean by physically meaningful universal constant is the smallest charge that a particle can have. Mm-hmm. And then the next one we're going to talk about is the Boltzmann constant.
Boltzmann's constant equals 1.38 times 10 to the negative 23rd joules per degree in Kelvin.
Joules per Kelvin, and it's the same units as entropy or disorder. It's used to measure kinetic energy of particles in gas. So half of the Boltzmann constant times the temperature of the gas equals the average kinetic energy of particles in that gas. Mm-hmm. All right, so then this next one is part of your job, vacuum permittivity.
Indeed. Vacuum permittivity is 8.85 times 10 to the negative 12th farads per meter.
All right, and There's a thing called Coulomb's law, right? And can you describe that and how it relates to gravitation?
Yeah, actually. So Coulomb's law looks a lot like Newton's inverse square law of gravity, except for this one applies to two charges. This is the product of two charges over the product of 4 pi times the vacuum permittivity constant, and the distance between those the charges gives the force between the charges. So this is another force constant, and that's why it looks a lot like the previous one, because gravity is a force, and so is a coulomb of charge.
Yeah, it's basically the only difference between gravity and this is that like charges repel each other. There's no repelling in gravity.
That's correct.
There's a very important distinction for reasons that we can't go into. So natural units, we said all these things are equal to whatever point whatever times 10 to the whatever, right?
Yeah, pretty much.
But then if you set the gravitational constant, the reduced Planck constant, the speed of light, and the Boltzmann constant, and the Coulomb constant even, the vacuum permittivity constant, and set them all equal to 1, then the elementary charge is equal to the square root of this number called alpha, and the electron rest mass is the square root of alpha g. So these two mysterious numbers, alpha and alpha g, show up. And what's the philosophical relevance, do you think, of that?
Okay, so the same in every system of units. That is to say, every natural unit system has this constant and another constant called the gravitational coupling constant, which essentially is equal to 1.75 times 10 to the negative 45th.
And alpha itself is equal to about 1 over 137. And this is what I think it was a physicist you mentioned earlier thought that this was an intrinsic property of the universe.
Yeah,
that it was exactly, it might have been him, that he thought it was equal to exactly 137. Now we know for better measurement that it's 137.0 something, and he crushed his dreams.
Oh, I know. I forgot. Now, it was either Enrico Fermi or perhaps it was Pauli. And I'm not sure, remember which one it was right now. However, this pair of constants describes the ratios between the constants, which themselves measure ratios. So it's like inception. It's like ratios of ratios, one of those things.
Oh yeah, for sure.
And again, these are unitless the way they're currently studied.
But they have to exist in physics. There's no way of getting around them. They're unitless constants, and that's what makes them so beautiful.
Indeed. Yeah. And actually, there's one more note here. What can we say about torque and rotational momentum versus force and momentum?
These are unitless the way that they're currently studied, but torque and rotational momentum versus force and momentum, they're completely different things, but they're measured using the same system of units. And it's only my view, maybe mine and some other people's, it's not a majority view, that we need a unit to put for torque, or maybe a modifier, something algebraic.
I don't know. Maybe one of our listeners will agree with you, and they can, support you on that.
Yes, I had to get on my soapbox.
That's quite all right.
Ratios are, at their core, a way of comparing two other numbers, and as we can see through centuries of technological advancement, have been extremely fruitful as a point of study. From pi to phi, and the speed of light to the elementary charge, ratios and their associated constants have given us our way of life. We do not know what constants and ratios lie in store, but two things are for certain. Ratios are here to stay, and they'll never stop surprising. I'm Jonathan.
And I'm Gabriel.
And this has been Breaking Math. If you want to support the show, where can we go?
You can go to our Patreon, patreon.com/breakingmathpodcast.